Hey everybody, welcome back. Today, we're going to destroy a bunch of bow tie inlays in the name of science. Many of you are probably well aware of what a bow tie key is, but for those that aren't, let's just start with a refresher so that we can get everyone on the same page. Known by many aliases, including butterfly key, bow tie key, dovetail key, the Dutchman, and plenty of others, it's also sometimes called a joint rather than a key. As far as I can tell, the names are interchangeable, and people tend to just pick the one they like and stick with it. So if I flip-flop back and forth in this video, I'm always talking about the same thing. No matter what the name is, it's an inlay that spans a seam or a crack to mechanically lock the two sides together. The key is cut lengthwise from solid wood and inlaid perpendicularly to the seam being stabilized. The result strengthens the crack and keeps it from getting worse over time. It also adds a decorative focal point that a lot of people like. I have a project coming up that will need to have some cracks stabilized, and that set me to wondering about just how strong these bow ties are and how much of a difference their shape makes. I have a lot of footage of me doing the initial testing with some blank pine boards as a control, but as a favor to all of you, I'm going to spare you that boring, rambling thought process and get right to the results. I found that with a 6-inch wide board, I could cut a triangle 2 inches in from either side of center and not only get the fracture to happen exactly where I wanted it, but it consistently happened at an average of 400 pounds of force. With the baseline sorted out, it was time to start mass-producing test pieces. I set up a stop block on my miter saw and chopped a pine board into a bunch of equal-length pieces. I made sure to cut out any knots to avoid as much variation in my material as possible. I marked up one board to find the exact center and the relief notches, then took some time to set up my miter gauge, fence, and a magnetic stop block on my bandsaw. With this setup, I could touch the corner of the workpiece to the fence, then slide it into the blade at an angle and come to a stop at the very same point every time. This gave me one repeatable cut that I could do over and over again to give me identical test pieces, and I didn't have to waste time measuring out lines on every single board. Next, I moved on to cutting out the bow tie inlays, and for that, I'm using my x-carve. I started out by carving one pocket and key for the most common bow tie shape to make sure that the inlays from my design file would fit together correctly. With the fit confirmed, I turned the x-carve loose. For the more geometric, straight line shapes, it's possible to cut them out by hand, as skilled artisans have been proving for years. But for speed's sake, and due to the complexity of the more intricate organic shapes, and not to mention that I have no skill, the x-carve is the way to go. I used a double-sided carpet tape to set up a solid fence before getting started to speed up the process of switching out workpieces. All I had to do was loosen the hold-down clamps, swap out the workpiece, and lock them back down. This way, I never had to re-zero the machine. Just swap and hit the go button. After all the pockets were cut out, I threw a piece of walnut in the machine and I let it cut out all of the inlay pieces in one go. Then, I used my bandsaw to cut the pieces free. And finally, I had a bunch of puzzles that were easy enough for my skill level. I made sure to do a good job of applying glue to every surface, then clamped the pieces in place while they dried. And here are the finished test pieces. With keys, the general idea is to make them wider at the ends and narrower in the middle to provide that mechanical lock. You'll notice the two on the top left break that rule, which means that they will really just be testing the glue strength. Also, all of these pieces are exactly 3 inches long, and whenever possible, they're 5/8 of an inch wide at the narrowest point. So the experiment has changed on me a little bit again. I went out with the entire stack of test pieces with the intent of ripping them apart, and I started with the weakest design, and that actually completely maxed out my scale. My scale tops out at 660. It broke at right about 660, which is 260 pounds more than what just a blank piece of pine broke at. So it's amazing how even this nothing badly designed piece added a ton of strength to it. That basically is just glue bond that added that amount of strength. So in order to continue the test, knowing that every other one of these would break at higher than what my scale is capable of, I had to revamp things a little bit more. What I did was take this broken piece that has this very convenient little finger hanging out and set it on my table saw and brought the blade up to just barely kiss the bottom of it, and then I backed it off just a little bit. Then I took all of the test pieces and made a kerf from the point of each of the notches. So now I have less than half of the thickness of that pine board being there. There is basically a 1/16 of pine and then a 1/4 inch of bow tie or butterfly, and that's all that we're going to be pulling on at this point. So I have 3 more control pieces that are just pine with that kerf in it. We'll break these. Hopefully they break at much less than that 400 pounds that a full width piece was doing, full thickness piece. And then we'll start ripping apart the pieces again, hopefully getting
a result of some kind that I can use. Because if everything breaks at above my scale, I'd have no data for you. Let's go back outside.
Now that we added the kerf cut on the back, the control boards broke at around 115 pounds, which is a much better starting point and made me optimistic that this was going to work. So with the help of my lovely assistant, we worked our way through all the test pieces, and one by one we destroyed them. The whole rig worked perfectly, and pretty soon we had a system down. I would work the lever and dodge flying debris, while Katie watched the scale and aimed the camera at it to capture the weight at the moment of failure. She would write down the last number she saw, then I would verify her number with the footage. This redundant system made it so that we would at least have some kind of data if one or the other didn't get a reading. Well, I'm happy to say that the camera did capture all of them, and Katie's observed numbers were at most only 13 pounds different than what the camera saw. We also found that putting the face of a shovel across the flat of the test piece kept the straps from twisting, making it much easier for Katie to keep an eye on the scale. I also like to believe that this helped deflect the force of the whiplash down into the ground a little bit faster. By the time we were done, we had some really interesting results, and only on the last and strongest test piece did I take a clevis to the ankle during the whiplash. Ouch.
All right, guys, the testing is over, and it's finally time for me to try to make sense of the results that I got here. Now, the first thing I'd like to point out is that I spent a ton of time early on trying to modify all these pieces so that they would break at a lower weight, knowing that my scale was limited to 660 pounds. Now, what I forgot somewhere along the way is that I'd done a bunch of research and found the right scale, and I ordered it, and then it was back ordered for about 4 months, so I canceled that and picked something else. Well, what I forgot is that the one that I ended up getting tops out at 1,100 pounds, not 660 like the one I had thoroughly researched did. So it turns out all that work I did to scale down and break weaker, in my mind, I didn't need to be doing that, but it turns out it was a great thing to do because we ended up with results of 857 pounds, 875 pounds, that way exceeded the scale that I thought I had. So I did a bunch of work that I didn't have to do, but it's a good thing I did because I did have to do it. And that's the best I can say about that. So let's take a look at what we've got here. First of all, looking at the control pieces, both of those broke within 1 pound of each other. We had 115 and 116. So let's just call it 115 pounds to break a pine board that's connected by 2 inches of material and cut through 2/3 of the thickness of it on the back side. 115 pounds to break that. The next lowest weight piece here was the whale. And I think the only reason for that is because the thickness of it at the narrowest point was only 1/4 of an inch. So it just didn't have enough meat in itself to hang on to anything. But that piece still did a remarkable job adding weight. We went from 115 pounds to 475 pounds. That's a lot stronger than it used to be. Now, the other thing I want to say is that all these numbers, obviously, this isn't a very scientific experiment because I don't have 20 of each workpiece to test and then average the scores. That would have been far more scientific. So take these numbers for what they are. I still think they tell a really interesting story. Now, jumping to the other end of the scale, we have the more traditional shaped bow ties. I actually made 2 of those knowing that that was the most common, so I wanted to get a little better idea of what it was capable of. And then we have what actually looks like a real bow tie. Shout out to Lakeside Woodworks in Kentucky for this shape. They kind of taught me about bow ties, and this is the shape that they like to use. These 3 were by far the strongest, and it's because of that double wedge shape that gives it such a mechanical advantage. One thing that really skews the results here is actually the simple bar shape. I expected this to break instantly. I figured that was going to be the worst thing and it would just sleeve that thing right out of the pocket and be done with it. And this is a testament to, holy crap, that's some really good glue strength. Similar story here, not nearly as remarkable as the bar. I expected the diamond to actually hold better than the bar because it just had more surface area for the glue to bind to. And that's kind of goes to show you that the wood has a lot to do with this. Maybe this piece of pine was actually weaker and it was going to break at 75 instead of 115. Those are the 2 that shouldn't have worked, and they still added a remarkable amount of strength over the plain pine board. Now, everything here, with the exception of one, broke the same way. The one is the turkey drumstick. That's the only one that actually tore the fibers across the grain of the walnut key. Everything else here actually broke in a shearing direction. They broke lengthwise. All of the pieces, if you look at them apart, are still a full 3 inches long, 3 inches long, 3 inches long from end to end. That's because the parts that broke lengthwise across the fiber. So the weak point is not the narrowest point in the key. The weak point is the shortest length of long fibers. That blew my mind a little bit. And that's kind of why all of these are great, all of these add strength, but if I was going to try to design the strongest possible bow tie key, it would be very similar to this traditional shape, only it would probably be a lot shorter on the ends. The taper would be a lot more subtle. That way, the shearing strength would end up being a lot greater. You would have a lot more long fibers holding together. And I believe that that would set a record amongst, the stuff that I have here. Take this for what it's worth. I don't claim that these numbers mean a whole lot specifically, but I think in comparison to each other, I think it's a fascinating little study, and I'm definitely going to be using some of what I learned here when I go to make my dining room table here in the near future. Big thank you to Inventables for supporting this video. They, with the x-carve, I was able to test out some more interesting organic shapes that I couldn't cut out with a chisel. Maybe somebody out there could, but I sure can. I don't have the talent for it. The CNC machine made all of these test pieces much faster and much higher quality than I could because I've never actually made a bow tie, a butterfly key on my own before. And that's why at the very beginning of the video, I actually had footage from a friend of mine. His name is Bruce A. Ulrich. You should check out his channel. He provided me with that pretty footage of that sliding barn door and that end table. So you should go down to the link in the description and go see those videos for yourself to see how he built those. I'm pretty sure I actually covered all of my bases, and that was more or less one take, so go me. What do you guys think? Please leave me a comment. I just think it was kind of fascinating the results I got. What shapes did you think were going to work? What surprised you? What shapes should be better than this? I know that the one I think was the coolest was actually the whale. And that's why I put it into my little tabletop over here that I made for my workshop. My wife actually drew this one out. I took a picture, I imported it into the computer, and I let the CNC carve that out. At this point, I feel like I'm rambling. Thanks for watching. Hope you guys learned something, and we'll see you next time.